Do you want a time warning?
Sorry?
Would you like a time warning? Or are you going to be okay?
I hope I get done way ahead of time, but if not, give me like 5 minutes.
5 minutes to be lost.
Yeah, just give me a hand wave at 10 or whatever. 10 minutes to go or something.
Okay, welcome back everyone. Next up we have Dave Sloan from the University of Oxford. He's going to talk about dynamical similarity, or things Dave will talk about a lot more about.
Yep. Thank you very much, Kareem. So yeah, for those of you who are in Tim's talk and Julian's talk and Sean's talk, you will have all heard the phrase, and Dave will talk and give you the details of this later on. This has meant I've had to rewrite this talk about 12 times over the last 2 days, so I apologize if it's somewhat disjointed and, if things don't come together. In fact, Tim and I were talking about this just a few minutes ago, and we decided that the statement for the conference was, here is an idea that Julian had with some diagrams made by Flavio, and Dave will fill in the details for you. The ideas I'm going to talk about today really come from the whole group. They come from Sean and Tim and Flavio and Julian and Enrique. These are really ideas that have come from everybody, but I happen to be the lucky one who got to do the maths on it recently, which was a lot of fun. Mostly going to be talking about a paper that's on the archive that I wrote recently. It'll turn up in PRD hopefully soon as the referee comes to his senses. Okay, so the headline. Within a lot of Lagrangian and Hamiltonian systems, there are a set of variables which are relational, they're autonomous, and they have friction. And I'm going to explain, hopefully, by the end of this talk, what all of those terms really mean in detail. And the overarching claim that I'm going to make is that these are the shapes that we've all been talking about in shape dynamics. Now, in this sense, you can think of my talk as being sort of very much compatible with Tim's, in which Tim tried to start with the shapes and build up the theory and build up a dynamics of the system. What I'm going to do is I'm going to sort of treat Hamilton's mechanics a bit like Wittgenstein's ladder. I can say that in the philosophy department. And I'm going to leave Wittgenstein hanging up in a tree and kick the ladder away at the last minute and leave you just with the shape dynamics that we derive from this system. So you can think of this as sort of being a bit of a Tim duality going on between our theories here. Although I think we've both got beards, so we're both the evil Tim. Okay, so yeah, as I say, the goal of this is at the end to find from within these Hamiltonian systems why shape dynamics can exist. Really, to me, this was a fundamental question because, Julian's had these ideas and Tim and I and all these people have been talking about them for such a long time. And it sort of hits you as like, why, if shape dynamics is true, why does Hamiltonian mechanics work so damn well? Right? Why can we just describe stuff as having scale? Why can we describe stuff with background structure if really the structure of the universe is such that we don't need it? And so hopefully by going through this, I'll show you how this works. So I'm going to start off with something we all know. Hopefully we all know Friedmann's equation. I've done a flat FRW universe, but to make Julian happy, I've put more than one type of matter in it, so there's some actual evolution. There's not just a scale factor that sits there and nothing ever happens. And one of the nice things about Friedmann's equations is when you write it down, someone might come along and go, well, Dave, I don't like your value of omega r. It shouldn't be 0.72. Well, if Tushar comes to me and says he doesn't like 0.72 as my value of omega r, what I can do is I can rescale all these parameters in a very specific way, effectively just rechoosing what my notion of scale is today, and come up with an exactly equivalent description of the universe, one that has exactly the same set of dynamics. All the observables are entirely compatible with one another. Okay? And this is something you really do learn in your first cosmology course. The scale factor is not a direct observable. We only observe relative changes of the scale factor. And so there's it's really a positive real degree of freedom in the description of the universe. This is an over-description of the possible sets of the universe. But then we all go back to GR class and we forget about this entirely. And when we do general relativity, we pretend that this description is not over-prescriptive anymore. We can mod out by diffeomorphisms, for example, but we don't anymore talk about this scale degree of freedom. But it's still there. And what I want to claim, and this is sort of similar to, again, what Tim was saying, it's hidden within the determinant of the metric. So changing the determinant of the metric, there are changes we can make to the overall scale of the system which will not affect the I suppose, relational equations of motion in here. And the reason for this is, in a very cartoon way, that if you have a variation of an action equal to 0, which gives you your equations of motion, just rescaling that action by a constant won't change your equations of motion. Now, it might turn around what some of the numerical values of some of these things are, but it won't change the relational motion. Dynamically, this is really interesting. In fact, I spent a large part of my sort of postdoc since I did my PhD working on how this leads to attractors in various theories of physics, why there are these preferred points in inflationary cosmology, for example, which seem to have explanatory power. We can argue about what I mean by that later, probably over a few beers tonight, if you really want to argue with me. But nonetheless, there is an interesting set of phenomena that come around because of this freedom. In a very similar situation, it's like rescaling laps. It's like your freedom to choose what your time coordinate is. It has an over-description of the universe. And what I want to say is that the mantra of shape dynamics really is that we have to use relational observables, and change comes from within, right? Change happens. It's something within the system. It's an intrinsic property. So, how do we do Hamiltonian physics? Well, hopefully you're all familiar with this, but in case anyone's a little bit sort of shaky on this, we start with configuration space, we make a cotangent bundle. So, again, my goal of physics, right, what I want physics to do is to have some description of the state of the universe here in terms of some variables, some observations, and what I really want to do, my entire goal of my life, is to put arrows on here. Okay? There you go, I have achieved my life's goal. Really what I want to do is tell you, given a state of the universe, in one configuration, what's going to happen next. Okay? And that's precisely what I think the purpose of at least theoretical physics is. To describe what that space is, I want to set that space up, and as Tim claims, this will be the shape space, and then to put a curve onto it. Okay? That tells me how things are going to evolve. So we can do this with Hamiltonian mechanics. We start with this cotangent bundle. We've got a symplectic form. That's just a 2 form that exists on this. And we have Hamiltonian vector fields. These are vector fields that are symplectomorphic. So you move the symplectic vector field along one of these using a Lie drag. By the way, I apologize for the fact I've got to use stupid letters here. It turns out Lagrange and Lie have the same initials, as do Hamilton and Hubble. So there will be sort of different fonts used to try and differentiate. But if it ever gets confusing, just yell at me. Okay. So we Lie drag this form, and if it's Lie dragged along itself, naturally along one of these vector fields, we say we've got a Hamiltonian vector field, or we have some conserved quantity, and our dynamics is defined through a flow on this space. As I say, I want to just put some arrows on here. Symmetries of this space are symplectomorphisms. That is, we want to conserve the Hamiltonian constraint, and we want to pull back onto a conservation of the symplectic form. Again, hopefully this should be somewhat familiar, but if I'm confusing people, don't worry, it will hopefully become a lot, well, there'll be more differential geometry, but eventually less. Okay, and where you have universal coordinate covers of this, you can come up with vector fields that do these Lie draggings for you, and so we're going to Lie drag the Hamiltonian along itself, and it's not going to affect the symplectic form.
So up there you mean you wrote LV of omega equals 0 and up there LV of omega equals...
So it should be F star of omega. I'm really sorry. That's a complete screw up on my part. It should be the diffeomorphism acting on omega doesn't rescale omega. Thank you. Yep. It should be LV of omega is 0 is what you're really looking for. The reason why I've written that is because we're about to generalize to that case. So before I actually get into how this works in general, before I go into the differential geometry of all this, I want to give a motivational example. And the motivational example for this, hopefully, is familiar to some of you. It's inflationary cosmology that Mary's just told us is all rubbish. The dynamics of an inflaton. Sorry. Oh, reminds me. So, the dynamics of an inflaton field on an FLRW, flat FLRW background is described using 2 equations of motion. We use the Friedmann equation and the Klein-Gordon equation. And the real thing I want you to take away from this is that although these are defined on phase space, notice that there is no scale factor, there is no volume of the universe anywhere in these equations. Okay? So we actually have a 4-dimensional phase space, but we only seem to have 2 degrees of freedom in this system. Why is that? So normally you'd have a 4D space, you'd have a constraint, so you can kill off one of these by solving the constraint, and then you should have 3 degrees of freedom. And the reason for this is that there's a symmetry in the system under the rescaling of volume. Okay? Just as I said, if Kareem had come along and said, I want the scale factor today to be 42 because that's my favorite number and I like Douglas Adams, you know, we can accommodate him in that way. I have put the curvature to 0 to make life nice and simple. This continues exactly the same way with the curvature. All you have to do is just rescale omega k in an appropriate way. So I will come to how you can do this for much more general couplings later, George. You do it with more general variables, but nonetheless, it's entirely possible, even in curvature, FLWK equals plus or minus 1.
So you're using here the Lagrange equation, not the Hamiltonian.
This is the Lagrange equations, yeah, so this should be P phi over V. Yeah, it's phi dot. So the thing I want you to look at this and you go, okay, the reason this looks nice to everyone who does physics is because it looks like a damped harmonic oscillator. So really, this is giving you a hint already, and again, this is why I chose this as a motivational example, is that we talk about this as being Hubble friction. Okay? Why? Well, if I describe the universe without this involved, we just have a harmonic oscillator. We've got a nice Hamiltonian description of that. We have conserved quantities. We have Liouville's theorem. All your nice sort of flow theorems continue. This guy is why you can't just write down a Hamiltonian purely for the Klein-Gordon field in this case, and you need the Friedmann equation. So, I did work on this with Alex Carici 6 years ago now, which is embarrassing because that's ages. You have a single field on a quadratic potential, as I said. You can write down the Lagrangian, and the Hamiltonian for this system does have a factor of the volume in it, but that factor you can pull out of the entire equation when you leave in sort of this description of the conjugate momentum to the scalar field. And you have a symplectic form, which you can write down here. And so I have a complete Hamiltonian description of my system just in terms of these two quantities, the Hamiltonian and the symplectic form. Okay. Now this system, as advertised, has a symmetry on the phase space. So under the action of this symmetry, v d by dv, p phi d by dp phi, we lead drag the Hamiltonian along itself. That's all nice and good. We've got a symmetry. But when you try and lead drag the symplectic form, you find it gets rescaled. Okay? So this is not a canonical transformation. This is what's actually called by mathematicians a non-strictly canonical transformation. And I got angry emails about this because I call this a scaled symplectomorphism because it rescales the symplectic form. But nonetheless, you write this on the archive and you get emails from people telling you, no, there's a term for this. It's called a non-standard canonical transformation. And what you find is that if you have your 2 form and you drag it along the generator of the symmetry, you find that it comes out rescaled. And what this does effectively is it changes the idea of length through changing the scale factor, but it also changes the idea of momentum. And again, this shouldn't be too surprising because momentum has units. You can then form the invariance of this transformation, and you find that the field and its velocity, note velocity, not momentum, but its velocity are invariants. And so what you then find is that the invariants the invariants of this system, which I've got down here, will form an autonomous system. That is, they will evolve one in terms of another without ever referring back to the scale factor.
Sorry, here you have, why you call it a symmetry?
Yep.
G, and then but shouldn't that be defined by what it does to the Hamiltonian and the other symmetry?
Well, it's a symmetry of the Hamiltonian, and it drags it hasn't changed the symplectic form, it's just stretched it. So I'm going to call that asymmetry.
Okay, so but then you're also stretching a little bit.
Yeah, I'm stretching the term symmetry to, I mean, it's a non-standard canonical transformation.
Okay, and also for the Hamiltonian.
So also for Hamiltonian, yeah. So what you can then do is say, I can want to express dynamics just in terms of the invariance now. Okay, I never have to refer back to the scale factor. How can I do this? Well, I have to do things with an odd dimensional phase space. So I can no longer have access to symplectic mechanics. I can't do Hamiltonian mechanics in the normal way because Hamiltonian mechanics is entirely based on having an even dimensional phase space. What do? Well, fortunately, what you can do is you can turn to the back of one of the appendices in Arnold's book on classical mechanics actually does this, and very few other places I've ever been able to find. And you find out that there's a form of mechanics called contact mechanics which precisely deals with these systems. When you do this and you look through and you reteach yourself how to do classical mechanics, and it takes you a few weeks, you find that you exactly get back the equipment you need. You can form a contact Hamiltonian, which does not involve the scale factor at all, and you form a contact form, which is like the odd dimensional version of a symplectic potential, and from these you can recover exactly the dynamics of the system in a way that never refers back to the scale factor in the first place. So in other words, if Julian had woken up one morning and just told us, the Hubble parameter exists but the scale factor does not, and had written this system down, this is the dynamics he would have to come up with to describe inflation within that kind of cosmology. Okay? All right.
Sorry, can you go back?
Yeah.
So, where's the eta? What is the role of eta?
The eta is like the symplectic potential.
Okay.
So it's a contact form, so it's a one form that lives on this odd dimensional space. Eta wedge d eta is a volume form on this space. And it's non-degenerate. Yep, this is written in... It's completely non-integrable, it's non-degenerate, it is... it's written in what's called Darboux coordinates, so a lot of your favorite theorems about even dimensional spaces follow through. Some of them don't, and I'll talk about the ones that don't and why they have interesting properties as a result of this.
One form, not the two.
So this is like the one form, this is like the symplectic potential. You want to hit d of this to get the symplectic form, but if I hit d on this guy would just die and I get d phi dot wedge d phi. Okay. Anything else that I'm doing that's weird? Okay, cool. All right. So this comes about, again, from sort of the shape motivation, what you want to say, and Tim nicked my examples on this earlier. But really what you want to say is, what do the terms in Lagrangian represent? So in other words, when we talk about these positions and the velocities, we really talk about them as measured by lab equipment. Again, you can all probably sing from the hymn sheet at this point, so I won't go into great detail on this. But the point really I want to get away from, or I want to take away from this, is that when we fix scale, it means we're going to take some function of these guys and set it equal to a constant. Okay, so Tim took the mean harmonic length, I think, right? Or the mean squared length, root mean square length of the separation of particles. What effectively you're doing then is you're taking this phase space and you're taking out a positive, a real scale from this. Okay, because you're modding out by the action of this logarithmic set of derivatives, or equivalently what you're doing is Tim could fix this equal to 1 because he's logical. Sean could set this equal to pi because he fancies pi being a nice number. Julian could set it equal to e because he likes that number, etc. Again, we'd all agree on physics. Okay, so there's a real number, positive real number in here that's free. When we mod out by this, we're going to take some r to the n, mod it by r plus, so typically we're going to get Sn. Okay, so typically we're going to be looking at our phase spaces, our shape spaces, as being compact spaces. This is lovely, right? Because if you've done a bit of geometry of compact spaces, you have nice things like flow theorems on them. And so you can prove properties of vector fields that exist on these guys. For example, the hairy dog theorem and things like that will tell you that there are always going to be stationary points and limiting factors under certain conditions. And again, the bold shape claim is going to be that this is how we really actually do physics. Okay, so how do we deal with this? Well, again, we want to talk about how we deal with conserved quantities and Hamiltonian framework. I'm first going to talk about how we deal with conserved quantities and then build up dynamics afterwards, because the first thing you ever deal with is deal with conservation laws. So again, we've got one of these scaled symplectomorphisms. This is what it does. You can,
Lambda doesn't depend on the points on phase space.
Lambda doesn't depend on the phase space. Lambda is just a positive real number. So it's going to rescale the symplectic form, and it's going to rescale, it's just going to stretch the Hamiltonian. Now I could have chosen to put a real number in front of the symplectic form, but I've just chosen a length along this vector field to travel. So I've normalized it so that that it scales the symplectic form to 1 times itself. This is just a redundancy in the description. So normally a conserved quantity is something where you take the interior product with the symplectic form, and that's the d of some field, and so you can just take dc and then you get boundaries, etc. You've got a conserved form. Okay, breach of the choir on this one. These commute with the Hamiltonian flow. What you can then do is say, if I've got one of these generators of dynamical similarity, one of these scaled symplectomorphisms, you can look at what the action of that is on one of these conserved forms, and you find that once again, the action of this, the Lie drag of one of these under this scaled symplectomorphism, also generates a conserved quantity. and it generates the same conserved quantity but not necessarily the same numerical value. So in other words, energies are mapped onto energies, angular momentum are mapped onto angular momentum, that kind of thing, but they might be mapped onto different values of angular momenta. Okay? So in other words, we're not going to break our idea of conserved quantities. Likewise, we're going to change the rate at which we understand coordinate time. Again, what you're doing by acting with one of these guys is you're just stretching the Hamiltonian flow. You're making it a bit longer, so in other words, what we're doing is we're changing local coordinate time. But that's fine because time is relative and all our clocks have to be constructed from physical dynamics in the system anyway, as Tim taught us about cesium atoms, so we're not really going to change anything about the flow on our shape space by doing this. You can find then, because you know how these terms transform and you know about how the local rate of time transform, you then find that the one form, h dt, is actually an invariant of the action of this transformation. And that sounds like an abstract mathematical result, but it has a profound impact on what your theory is, because what it then tells you is that the Lagrangian is dragged onto itself. Okay? So in other words, under the action of one of these flows, we are going to map solutions to the equations of motion onto solutions to the equations of motion. So I'm not breaking the equations of motion of my system in doing this. All I'm doing is reparameterizing them.
Which symplectic potential are you using there?
PdQ. This is entirely Hamiltonian. This is entirely Hamiltonian at this point, so I'm just going to use the standard PdQ. Symplectic potential. You could actually use just about any, really, but I'll go into the details with you later, but that will take a while. So in other words, equations of motion of the invariance of this are preserved under its action. So not only does it not change the value of phi, it doesn't change phi dot, phi double dot, phi n dot, whatever. Okay, so a summary. We have a system of invariants. They have an autonomous evolution. What does this mean? Well, it means that if I want to find the equations of motion of G, they're entirely determined by in terms of invariance. So in other words, the invariance of this, because it's a Lie derivative, they form an algebra. And so any derivative, any evolution of one of these must be written entirely in terms of the algebra of these objects. Okay? Now I've formed the set of invariants to make this algebra. This must be a lower dimensional space than the original space because there are some things that are not invariant. So in other words, what I've done is I've taken out something that represents, and I'm going to claim it represents scale, and I've said that all the scale-free objects evolve only in terms of other scale-free objects. I can describe their dynamics only by referring to other shapes. The action's been stretched, we've messed around with the time coordinates, but we got back our conserved quantities the same way, and by construction, this space of invariance is smaller than the original phase space. There must then be redundancies which are generated by the flow of this one-dimensional vector field, and the question then is, could I just come up with a theory where I deal with the invariance directly, and I never have to refer to this background structure in the first place? Well, in order to do this, I do need to understand the physics of an odd-dimensional space. Now, I didn't know how to do this, so I went and looked it up in books, and it turns out that contact dynamics is the way that you can do this. There's about 3 papers on the archive that are of any use when you try and work out how this works, and there's sort of tiny little bits in textbooks here and there, but you've really got to sort of struggle through it for yourself. Again, you have one of these contact forms which looks like a symplectic potential. You can make a volume form out of it by taking taking wedge products of this with itself as many times as necessary to cover your entire space. Notice this is just like what you do to make a Liouville form on a Hamiltonian space, but there would be a D in front of this at the front. Generally, there exist Darboux coordinates, so you can write down a unique representation of what your shape space is in terms of these. And your dynamics comes from a Hamiltonian just written in terms of these guys. And you have equations of motion that look just like the Hamilton equations that we all know and love, but they have extra terms in them with reference to this special coordinate which has no conjugate position. It's like it's a momentum. It's a position with no conjugate momentum, effectively. except for it's got a minus sign, so you can view it as a momentum or a position, depending which way you want to wake your hands around. So in other words, this looks like a system that's ideal for describing dissipative systems. So it's ideal for describing frictional systems. In general, you can actually do this in Hamiltonian mechanics, right? So there's actually a myth that you can't deal with dissipation in Hamiltonian mechanics. That's not actually true. You can, but normally what you'll do is you'll take Lagrangian and introduce a time factor into it. You'll make it explicitly time dependent. What we want is one step further. We want time independent functions that describe our motion. So in other words, you can do this, but at the cost of introducing an external time parameter. But Julian will jump all over you if you bring in external time into his systems. He'll be very upset. So we don't want to do this. And so we're going to start by describing these contact systems. And as I say, I want to give a shout out to these guys who wrote some papers on this, because they're really the nicest ones to read if you're trying to get into this. Look these guys up on the archive. There are some very nice places where they've looked at how you can do, for example, statistical mechanics using these frictional systems. Okay, so we've got dynamics of an odd dimensional systems. How do we relate this to the invariance? Well, what I want to claim now is that this does exactly describe the dynamics of the invariance, of the shape space that we all want to sort of understand. And what we need to do then is create a contact Hamiltonian from the invariance. We need a contact form that we made out of the invariance, and then we want to describe relational motion just in terms of these guys. And again, for the next few slides, I'm going to show you how you do this.
You comment on the relation between we have two kinds of energy, right? Then in the original variables, and then one we have the friction.
Yep.
So, and how are the two energies related in a way? Is there a direct?
Like this.
Like this. Right.
Yep. So you can actually prove how this works. So there's an algorithm for finding the shape space from within one of these systems.
Yeah.
What you do is you identify the dynamical similarity as being a vector field on your original phase space. You find the space of invariance and the one representation of the non-invariant. You form the contact form by just taking the interior product of your symplectic form with this vector field and divide out by one non-invariant. The reason you divide out is so that you get an invariant form here. And then you find the contact Hamiltonian. It's just some rescale, so some real number times the symplectic Hamiltonian divided by this invariant. So there's entirely a proof process that will give you the relationship between these two. It's algorithmic, it's prescriptive, and it gives you a complete description. And you can prove that this works. You just really what you do is you just use Cartan's identity an inordinate number of times on your equations of motion, and you find that the equations of motion that you get in the contact system are exactly the same equations of motion as you got in the Hamiltonian system. So now that I've got this contact system, what about if I wanted a symplectic system? So in other words, if shape dynamics is true, why is it that we can always embed this within a Hamiltonian system? Well, it turns out that you can use a process called symplectification. These forms, these contact forms, are unique up to a choice of scale. So up to a real number that you can stick in front of them. You promote this real number to a variable, to a dynamical variable, and then you recover exactly a symplectic form on the extended space with this extra real number, and you recover exactly Hamiltonian mechanics under these identifications. And what it looks like is the new dynamics you've got is conservative, but you see that there's an expansion along this new real degree of freedom that you've introduced by hand to symplectify the system. So in other words, if you give me a shape system, if Julian had just dreamt up shape mechanics, ahead of Hamilton, and Hamilton had gone, oh my god, how am I going to turn this into Hamiltonian mechanics? He would have to actually come up with this process, and he'd be able to embed all of Julian's dynamics within his own system. Okay, so why do I call this friction? Well, the contact Hamiltonian itself is not actually a conserved quantity in general. It has a dynamics. So it has a dissipation as it evolves. Okay? And generally the dissipation is proportional to itself. This is quite nice for those of you who deal in GR, because the GR Hamiltonian is exactly 0, so it turns into a conserved quantity again. In cosmology, the Hamiltonian is a constraint. The constraint's equal to 0, so there's no evolution of this. But in general, we want to be able to do this for every system, right? We want to be able to shapeify every possible Hamiltonian mechanics system we can get. Likewise, the shape volume. So the volume form on a shape space, this is the measure that Julian was talking about. you can form exactly out of this one form. You follow it, you just follow your nose, you make a volume form, and you look at the dynamics of this volume form, and the flow of the volume form, again, along in evolution, along a Hamiltonian vector field, which gives you time evolution, tells you that this thing actually gets rescaled. And that's precisely what leads to this focusing. So Julian drew these really nice pictures of the three-body system, and over time it gets further and further down a little hole into this. You might say, how does that happen? Well, it's precisely because there's a focusing of this volume form. Wherever you sprinkled your initial conditions, eventually over time you're going to end up in one of these attractor points.
So can you remind me what A is?
A is, so we have a contact form. Where are we? Where have I written this? Yeah, A is, so you have, is it on the previous slide? Yeah, there you go. So generally your contact form is just dA plus x wedge dy. And so generally what you're going to be saying is that eta is equal to, what is it, minus dA plus dx cross dy. So there's one privileged direction in any contact space which doesn't have the equivalent of a conjugate momentum to it. So in cosmology, this turns out to be the expansion of the universe, because the scale factor, which would be the conjugate position, is not observable. In n-body systems, this is going to be a bit like the dilation, because again, the position, the overall scale, is not going to be observable. Yeah, sure, yeah.
Because you call it focusing, so
yeah.
What are the conditions under which this factor is monotonic, this DH is monotonic?
Depends on the contact Hamiltonian. So it depends on the physical system you're considering. If this is always positive, it's monotonic.
Yeah, but what does that mean in terms of like the potential?
Well, if it's like a squared, so if you get like Hubble squared, for example. I mean, in flat cosmology, it's always true. For example, in the n-body system, it's always true. But it's not universal. In closed cosmology, it's not always true. So there's focusing and unfocusing. Yeah.
Should we already understand how this is consistent with the time reversal invariance?
This is entirely time reversal invariant, because if you put a minus sign in front of this, you'll get the exact dynamics in the other way. So this isn't taking many solutions to one. It's taking many solutions to many solutions, but in a smaller volume. Okay, so again, Julian talked about these very, very sort of special points in the evolution of shape dynamics, which we called Janus points. Compare them with a Janus point, which I think Sean came up with a few years ago, which was a bit like, well, anyway. I still think this comes down to mishearing and misspelling things, but, you know, nonetheless, we've ended up with two different versions of the same idea. But the thing to notice is that both the evolution of this volume form and the contact Hamiltonian depend on this one parameter, okay? And in general, so this is a little hand wavy, but I'll show you examples. These are zero somewhere along a trajectory. So along every trajectory, there will be a point at which the volume form of neighboring solutions is no longer being pulled towards anywhere and no longer dissipating. It's exactly symplectic locally. Likewise, there'll be a point along each of these evolutions, at least one point, where the energy is locally, instantaneously conserved. So just for an instant, the system will look like there's no friction. Okay? In a harmonic oscillator, damped harmonic oscillator, that's when there's zero velocity, when you're all the way out and you're just turning around. That is the equivalent of local geodesic motion. Okay, so locally you're feeling no friction. So locally forces really like this aren't acting. But away from this point, this volume form focuses. And that's what Julian is really calling the local arrow of time in his n-body systems. And once you embed this in a symplectic theory, once you symplectify these contact systems, you get back all the things you know and love, like Liouville's theorem and all the lovely flow equations. So in other words, again, had we started with shape dynamics and discovered Hamiltonian mechanics by accident later, Liouville would have had to wait until you could do this in order to prove all his theorems. But nonetheless, they're all nice and true still. Okay, so what have we gained? Why the hell have I done all this? Well, the idea is that we can start with a system that has one of these symmetries in it. We then identify this set of invariants. So again, in the n-body system, we start with this system that has a scaling invariance, where we can take the scale of the separation, the size of one of these island universes, and rescale it. The set of invariants, the set of shapes then we find are autonomous and appear to experience friction. There's a notion of an emergent error of time within a solution, and we've generalized the idea of a Janus point. But the question you should really ask me then is like, okay, you've invented these, why should I care about them? Right? How often do you come across something that has one of these obscure symmetries in it? Well, the answer is they're everywhere. In fact, if you believe in shapes, if shape dynamics is right, this is all of physics. All of physics should have this invariance under a choice of unit, under a choice of scale. As an example, you can see them anytime a Lagrangian is homogeneous in one of its variables, you're going to get a dynamical similarity. I can show you how to construct it. In the n-body systems, there's a dynamical similarity. I can show you explicitly how to construct it. Bianchi cosmology, it's there. In the interior of the Schwarzschild, it's there. In fact, for generic potentials, there's a way of doing it where you have to be a little more clever, but nonetheless it exists and you can find them. And there are loads more systems. Basically, every system I've managed to look at, you can find one of these symmetries in it. You have to be a little careful about how you define it, but nonetheless, it's there. And yeah, accost your favorite shaper for a greater explanation of why we all believe in this. So, as an example, let's talk about the n-body problem. But I'm a bit more ambitious. Let's not just talk about the Newton potential. Let's do all the potentials, except for 1 over r squared, which is a bit odd. But again, I can do this, but it doesn't quite fit in this framework. We can write down our Lagrangian. We can describe this in terms of a scale and in terms of some shapes. We can write down a Hamiltonian system that describes the motion. Then we can find the dynamical similarity for this. You can either do this by being very clever and thinking very hard about what you do, or you can do it my way, which is you just brute force vector fields till you find the one that works. After you do that, you can identify then the invariance, just following my algorithm, find the contact form, and then you find that there is indeed this autonomous set of equations of motion of the shapes. Okay, these are the angles of the triangle that Julian was talking about earlier, but this is generalized to the n-body system with any potential that you choose that's homogeneous of degree n. And just to prove what Julian's been saying for a very long time, there is a totally autonomous shape dynamics. You can find this as a second-order differential equation of the shapes, and you find that you need a point here and a direction completely determines dynamics. So once you look then at the n-body system, you can then say what are the attractors of this system. You find that because there is friction in this expansion of the system, you're going to find that there's a monotonic friction in the n-body system, again just by looking at the form of the contact Hamiltonian. If the force is repulsive, so if you have a positive power, if these guys are being pushed apart, you find the attractor is all the point particles are equidistantly separated on a sphere. If the force is attractive, you find they all fall further and further down the wells of shape space. And again, these are unstable or stable attractors depending on whether or not you've got a repulsive or attractive force. And there is the first really cool possibility of a shape prediction here, is that if you know these attractors exist, you can then start with a measure formed out of this contact form to make a volume form and say what fraction of solutions fall down the different attractors that there are in this shape space. So in other words, if I give you 1 billion particles, all of which are interacting with some attractive force, we should then be able to predict what the sizes of clusters should be. So on average, how many particles are we going to find in a little local cluster? Again, this is highly ambitious, but perhaps this could eventually lead us to predict the average number of stars in a galaxy, for example, or the distributions of numbers of stars in galaxies. Again, that's a massively long-term goal, but be ambitious. Okay, as advertised, I will do Hamiltonian cosmology. I'll do this very quickly because Kareem will get angry at me. Yep. You have a metric, a symplectic structure, a Hamiltonian, all given to you by GR. You identify the dynamical similarity of this system. Again, you can just trust me that this hits this and gives you it back, and this hits this and rescales it. Then you can prove a version of what Flavio, Tim, and I did quite recently, and that is that there's an autonomous system of the shapes in this. You can evolve this system in terms of the invariants. I've just written these down here just so you believe that they exist. And you find the equations of motion. And these equations are written in bizarre little letters because, you know, I want it to be weird. But nonetheless, when you look, we only actually have 1, 2, 3, 4, 5 equations of motion for a system that should really have 6. And the reason is, as Tim was talking about earlier, there's this parasitic equation which tells you the evolution of scale, which you can put in after the fact. So in other words, given this system, I can completely find the evolution of any setup for all time, for as long as I possibly want, and then after you finish doing that calculation, you can then say, and I want the volume of the universe today to be 72, put that in and solve what the volume of the universe was at all times. If you do this, you come up with a dynamics as advertised on shapespace, a curve on shapespace, and you find that at the singularity, there's nothing wrong with your equations of motion. So Hawking and Penrose proved that if you have a scale system, what you find is that you can't continue this evolution. The metric description of gravity breaks down at that point. What we have found is that that is entirely true. Okay, we in no way contradict Hawking and Penrose, God forbid. What we actually find is that's true, but it doesn't matter. Because the equation that breaks down is the equation that tells you the evolution of scale. And we don't care about scale. The shape evolution continues entirely through this position and goes out the other side quite happily and continues on its merry way. So what did we do? Well, yeah.
Is that also the point where you recover Hamiltonian dynamics?
You locally recover Hamiltonian dynamics actually at the point of recollapse in this system. Not there. So it's not quite the same. I'll go into this. I'll go through this in questions properly if you're still confused. But yeah, it's a bit. That's the difference between Sean's Janus and Janus points, which is why Janus with an I. Yeah, Jesus Christ. Okay, so the singularity isn't avoided. It's classical at all time, and you get GR on both times. And as I said, you don't contradict Hawking-Penrose. You can completely evolve geodesics through here. You just break the geometrical interpretation of GR. But nonetheless, the deterministic equations continue perfectly happy. Okay, I'll wrap up in just a minute, as Kareem will get mad. What about if I want to change coupling? So in other words, so far I've only talked about systems that have a single interaction. And, you know, this is a real problem for actual physics, because I don't know about you, but I feel more than one force acting on me. Okay, there's gravity and there's some wonderful normal force which stops me falling through the floor. So, what if we had more couplings? In other words, we can expand our potential in terms of a Taylor series, for example. And we can just write down there's some number that describes each coupling of the terms in our Taylor series. These can be positive, negative, etc., etc. Well, remember that nonetheless these couplings must be measured from inside cosmology, you know? So there's a big sort of myth that people in GR seem to have believed for a long time, and that is the idea that somehow God came down from heaven and handed us G, C, and H bar. This is not true. We measure G, C, and H bar. Experimentalists spend a lot of time doing this, and we all ignore the fact that they put a lot of work into this. But these are observed quantities that you should be reading off a curve in shape space. So, how can we do this? How can we take care of this? Well, this is work in progress, and Sean and I have talked about this quite a lot. But you can extend your dynamical similarities onto a space of couplings. And what you've find is actually there's a flow then, not just under changing scale and changing your idea of momentum or time as a result, but also you find that the effective values of the coupling constants will evolve too. And this has a lot in common with what Astrid was talking about earlier in terms of, I mean, it's a real shame she's not here because I've said you should ask her about this. But it has a lot it's got a lot in common with the functional renormalization group and RG flows on these spaces. Again, Sean, I think, is really the expert in the absence of Astrid on this stuff. But nonetheless, and Tim, yeah. But nonetheless, what you find is that it's not the couplings themselves, but it's the ratios of them as, you know, normalized by mass dimension that actually determine the shape dynamics. And so if you have two sets of couplings, you know, and you don't like the strength of the fine structure constant, you can change the universe so that the fine structure constant changes, but you have to also change the cosmological constant and the Newton constant and everything else to do this. Okay, so to summarize, there has been this hidden symmetry in many physical theories, which I've called dynamical similarity. You get a relational shape dynamics which is autonomous, it never refers back to the scale. We can extend problems, for example, things in the scale variables that were problematic like the Big Bang, not a problem for us, we can go straight through them. This uses a frictional contact dynamics in odd dimensions, and we can always embed it back in the symplectic system. And I want to finish here with what I'm going to call the shape conjecture. And it's the real conjecture of shape dynamics, I think, is that all of physics works this way. Thank you.
Thanks, Dave. That was fascinating. So the students as per usual?
In Noether theorem, actually, if you have a symmetry, you have a conserved quantity, right?
Sorry?
Noether theorem?
In Noether's theorem, yes, you have conserved quantities, yes.
So in this case, we have a conserved quantity?
Yeah, you don't break your conserved quantities.
But what is that?
What's the conserved quantities? No, this is not a gauge transformation in the physical sense. So this is an interesting question, right? Normally when people talk about a gauge transformation, they're talking about a symplectomorphism. This is not a symplectomorphism, this is a scaled symplectomorphism, so it is not generated by, basically you can't generate this by hitting a Poisson bracket with a vector field. So you don't get a Noether charge.
And actually, when you change the scale, also you have to change the scale of the physical constant.
If you have multiple physical constants, yes.
In that case, I mean, you have to actually assume that physical constant is some sort of field variable, or?
What you can do is you can embed this within a system of physical constants in which the physical constants have a prescribed evolution. But that evolution is prescribed by the shape dynamics itself. So in other words, this works entirely fine if you can make a gauge choice in which one of the you choose your favorite constant, it is constant, you can always describe physics in that way. Or you can choose to have scale remain constant and your physical constants change in size. These are equivalent descriptions, redundant descriptions of the same physical dynamics.
Other questions? I actually have a question.
Yeah. You're not a student.
So with one ion quantization, is there Hamilton-Jacobi formulation of contact mechanics?
So this is the thing I made especially for Astrid, who then left. She gave us some challenges in shape dynamics. The first thing is say something about quantum gravity. Well, I mean, this is really a key question, right? How do you quantize contact dynamics? I don't know yet.
Is it Hamilton-Jacobi formulation? No.
I don't know.
Because if you had one, though.
Yeah. I mean, Sean and I have talked about this a little bit. I mean, the thing is, you want to form a bracket, right? And you want to form, but you've only got a one form, and the one form isn't like a symplectic form, so it's not you've got an odd dimensional space. So what's conjugate to one of these things? You know, how do you do this? Tim probably is about to answer this.
Yeah, you quoted Alessandro Bravetti.
Yeah.
And him and Alejandro Chung have looked at representations of that algebra, of the algebra of the elementary variables of contact forms, and they came up, I think, just for the book coordinates, but they found a representation for them.
Yeah. So the probably is. I mean, there must be a way of doing it, right? If nothing,
the analog of finding a representation.
Algebra. Yeah.
It's a technical, not a conceptual.
Quiet, you. I said you gave distractions.
Just a comment which may or may not be useful for you. Eisenhardt's book, Continuous Group of Transformations, 1937. Chapter 6 is about contact transformations.
That's incredibly useful. Yeah. So far I've been working out of an appendix of Arnold's textbook on classical mechanics, and about 3 pages on. Now the whole. Actually, to be fair to the mathematicians, there's a beautiful section of differential geometry on the archive that entirely deals with contact forms, but they don't seem to do the physics of it. They do the differential geometry of it, which has well, you can lose yourself just reading these powerful, wonderful theorems in there, but I feel like I go into these, I have to confess, I go into these papers looking at beautiful maths and thinking, what can I make physics out of this, which is, might not be the best way of doing things.
Yeah, so you mentioned extension beyond the Big Bang.
Yep.
Semi-answer of a second.
Yep.
This is a claim that's often made, and I'd like to understand it better, what it means. In the sense that if I'm just in GR and I look at the Friedmann equations, or whatever equations I have for a Bianchi model, it's quite often the case that I can extend the solutions beyond a equals 0, and that actually nothing goes wrong in the equations. So you could make, at least at face value, an extremely similar argument in GR. I mean, there you would just say you're rejecting the extension of these solutions because, of course, the Ricci scalar blows up, or other components of the curvature. But if I'm just concerned with the solutions, often they can...
No, so the technical thing that we proved, and again, I didn't do this in detail here, which is why, but I've talked about this several times, is the equations of motion you get is an ordinary differential equation system which is Lipschitz continuous. So it is, in the differential equation sense, deterministic and unique, the continuation. Now, the problem you normally have with continuing GR solutions through the Big Bang is you have to make an ad hoc choice of, do I take A to minus A, or do I just reflect A? What do I do? Or, I mean, or you could just take A to A over 1,000, or, or whatever, add 17 to it. You have to make a choice there. The point is that within the GR system, when you go to the shape description of GR, the equations not only tell you what to do away from the singularity, they're actually Lipschitz continuous at the singularity. And so you have no choice in how to continue this. So in other words, it's a prescription that's given to you by GR. We're not putting anything new in by hand, which a lot of these continuations are.
Yeah, I'd be very curious to see how general this property is, also in homogeneous models.
Read the paper. It's out. I mean,
thanks a lot. That was great. But so it seemed in this formalism there was this dynamic similarity you've got to find, and it's got to preserve the Hamiltonian and scale the symplectic form. And it seems like you do that you said it yourself. You've got to guess, intelligently guess what it is. Whereas like other forms of doing this, we know what you want to do is mod out by R plus. And it seemed like there's a much more practical way of doing that in the three-body problem, and it's intuitive. How do you relate these two?
They're exactly the same as what Tim talked about how you do it. They agree entirely. In fact, the dynamical similarity he gave on his slides are exactly the same ones that I derived here, but in a more generic concept.
It appeared that was algorithmic.
So this actually is algorithmic. I mean, I was being a bit glib when I say that you do this by brute force. But what you want is a vector field on your phase space, okay? And you want it to preserve the symplectic form. And there's only so many choices you can make that conserve the symplectic form. And then you say you want to conserve the Hamiltonian also. And that actually defines for you almost always, in fact I've never found somewhere it doesn't, a unique vector field that does this. So it's entirely prescriptive.
That's promising.
Yeah, well, it's...
Thanks, Dave. That was really marvelous. This is a really crude and sort of low pay grade question.
Excellent.
But you made a lot of use of sort of flow theorems and Lambda differential geometry and stuff. I can't off the top of my head see how much of that relied on compactness assumptions and things. What happens when your phase space is infinite dimensional?
Infinite dimensional, all bets are off. I don't know how to deal with the infinite dimensional case. So, I mean, I think, and again, Tim talked a little bit about this, there might be, I mean, there's probably a way to implement this in GR, but you'd have to be very,
Turn the crank.
You can turn the crank in GR, and it will work.
It works exactly.
Yeah.
The problem with GR is that the compactness thing no longer
It's no, and so it's not, So I mean, in the n-body problem, I'll Julie in a sec. But in the n-body problem, for example, it's really sort of encouraging to us that shape space is a compact space. The reason why this is encouraging to us is because you have a finite measure in a compact space, which means when you talk about typicality, you're no longer running into the problems that Simone talked about with measure problems. In fact, Simone talked about much harder ones in infinite dimensional spaces and all kinds of, But nonetheless, in a non-compact space, there's an infinite number of possible ways you can take limits that give you different answers to these questions. Here, there should be unique up to a class, perhaps.
Yeah, I think I'm probably just going to say again more or less what you said. There's two problems with infinity. One comes from scale, and shape dynamics solves that completely. Shape space is compact. However, all of the ones that we can really handle. But if we want to do statistical mechanics and make probability things, we can only do it if it has a finite number of dimensions as of now.
Yeah.
We need some way. Correct, Dave? Is that what
yeah, I mean, well, again, but I would come back to actually, I mean, I'm going to lean on George for this, but you know, George will argue there are no real infinities, so perhaps what we should actually be doing is describing a finite number of modes of GR, not all of field theory, for example.
Yeah,
you know, some ratio between the longest wavelength and the shortest wavelength in the universe will give us a maximal possible number of modes we should be describing.
Yeah, the thing that I feel is very attractive, which is really I got that first from you, Dave, is that we never get to infinity, but we get to a stage where more and more dimensions show up, degrees of freedom show up, but they show up in the late time evolution.
Yeah.
This is where metrology, in the actual universe, the metrology is getting more and more fantastic.
Yeah.
I made that point already, that you couldn't build a cesium beam before the first supernova went off. Now you can.
Yeah, I mean,
now they're building ones with optical clocks and things like that. So my suggestion, and I use this expression, in the fullness of time, you will see more and more of these degrees of freedom. And maybe that's the way we approach, it's a potential infinity where we can keep on going with luck, but we'll never, of course, ever get to infinity. It's Hilbert's Hotel.
I mean, I agree fundamentally with that. I would just want to say, while I've got a bunch of philosophers here, Tim defined this second in terms of oscillations of a cesium atom. So were there seconds before there were cesium atoms? And what were they, and how would you define them? And how would you define lengths when nothing in the universe is staying the same length in a Friedmann equation, right? How would you define a meter? How do you define a cesium? I mean, there must be sort of proxies and ways you can do this, but yeah, I think this is a real challenge.
For millennia, it was the rotation of the Earth.
Sure. But again, I mean, as you say, the part about clocks is that they march in step. The important thing about the rotation of the Earth is that the rotation of the Earth divides the rotation of the Earth around the Sun in terms of the fixed stars by 1 in 365. That's the really sort of nice thing about it, to use it as a clock, right?
But yes, of course, it's terrific. And then, of course, there's this interesting thing that the tropical year, from one crossing of the equinox to the next, the spring equinox, that can differ by up to 20 minutes.
Sure, yeah, absolutely, yeah.
We have time for one more question.
No, please.
Just another question about cosmology for curiosity.
Yeah.
If the solutions go through the Big Bang, do you see a way of matching inhomogeneities across the Big Bang? Or the Big Bangs? Because that's usually a big problem in bounce models, right? Because
no, this
you have no idea how to match things across.
So there are a couple of things. Again, this isn't the cosmology talk, so I didn't go into it in any detail. So please, there are two possible things you can talk about here. I mean, the first is the one I always fall back on, which is the BKL conjecture. And that is that the dynamics of all of cosmology becomes local, oscillatory, and vacuum dominated. And so for those of you who don't know this, Belinsky, Klatnikov, and Lifshitz conjectured this in the 60s. And recently there's been a ton of numerical evidence that if you start with an inhomogeneous universe, correlations between separated points turn off as you go back towards a singularity. So in that sense, you might be able to point by point evolve your universe through the Big Bang, and then the inhomogeneities will continue because they're point, each homogeneous universe is a local point which is not the same as its neighbor, and then as you move away from the Big Bang, the inhomogeneities are continued that way. However, there are space-times potentially which might not satisfy the BKL conjecture. We don't know this, it's called a conjecture. In that case, we really do need to look at the full PDEs and look at the definition of the PDEs and the continuity of the PDEs across this point. That's going to be a much harder project to do, but it's something I think we are, well, I don't know about Tim, I'm volunteering Tim to help me with this over the next few months.
And on that note, let's thank